Section 8.2 is on testing a claim about a proportion. And this first method is the normal approximation method. It requires a simple random sample, a binomial distribution, where we would have that binomial experiment, so if there's fixed independent trials n, the constant success p and failure q, which is 1 minus p, how those don't change, we have those two options and whatnot. The number of successes, n times p, has to be at least 5. The number of failures, so n times q, must be at least 5. To apply the sampling distribution such that the mean of the sampling distribution of p hat is equal to the population mean, and the standard deviation of the sampling distribution of p hat is equal to the square root of n times p times q. The test statistic is z is equal to p hat minus p divided by the square root of p times q divided by n. And we want to obtain the p-value and the critical value from SAS. A confidence interval should be used to estimate a population proportion, and the p-value or critical value method can be used to test a claim about a proportion. Alright, so the confidence interval is to estimate the actual value, and the p-value or critical value method is used to test a claim about it. So, for example, a study of sleepwalking or nocturnal wandering was described in the journal Neurology, and it included information that 29.2% of 19,136 American adults, have sleepwalked. What is the actual number of adults who have sleepwalked? So, this uses the formula of p hat is equal to x over n, where x is the number with the characteristic. Here we are given the proportion to be 29.2%, so 0.292. This would be equal to, we don't know x, but we know the total number was 19,136. So, just simple algebra, we would solve for x by multiplying 0.292 times 19,136. Toss in that multiplication to a calculator will give us a value of about 5,587.12. But because we are looking at the number of successes, you can't really have a decimal amount of people. So we would then round this up to be 5,588 people in this particular case. For example number 2, if we continue this example, so n being 19,136, p hat 29.2%, would a reporter be justified in stating that fewer than 30% of adults have sleepwalked? Let us use a 5% level of significance to test the claim that t, for the adult population, the proportion of those who have sleepwalked is less than 0.30. So, for this, we had a simple random sample, as we just said on the last slide. So, simple random sample. We had that simple random sample, and it's binomial. Since we had that 19,136 trials, they're independent. We had a specific success and failure rates, and neither of which changed based upon the experiment occurring. And we could test the normality. We just found on the last slide that n times p was that 5,000 740.8 point 7, excuse me. Oh, I know what it is. This was supposed to be times. Let me actually write out the formula. That might be more helpful than me just writing the number. So that formula for this, we are using now 19,136 times 0.3. This gives us a value of 5,740.8. N times Q, so 1 minus P, this will be 19,136 times 0.7. And naturally, if this is greater than 5, this is definitely greater than 5 as well. This will give us a value of 13,395. 0.2 is what this one rounds to. So both of those are greater than 5. So then we could say that this is approximately normal. And then we can, the population, excuse me, is approximately normal. And as such, let me just write this out. And as such, because we just found it to be approximately normal, we could then continue on with the test. So if we were to toss these numbers into, well, we first need our hypothesis test. Actually, let me write that. The null hypothesis is that the proportion is equal to 0.30. And the alternative is that the proportion is supposed to be less than 0.30, based upon the way this is written. Alpha is 5%. If we were to toss this into the formula, or into SAS, and we don't need the formula, but this would be Z is equal to, and let's see, Z would be equal to 0.292, which is what p hat was, minus 0.30 divided by the square root of 0.30 times 0.70 divided by 19,136. Tossing this into a calculator or just putting this hypothesis test in SAS will give you a z-score of about negative 2.41. And the associated p-value will be 0.008. So if we were to very quickly do a very basic drawing of this, the mean of this, as I said, was 0.30. And we want to find the value, well, this is going to be less than 0.30. Our value of p hat was 29.2. So that will be about here-ish. We want this area below it, which a test statistic of negative 2.41 is definitely going to put it below this, and it gives us a p-value of 0.008. And as such, we could then state our conclusion to this hypothesis test, and that would be written out as, I'll write it down here, at the 5% level of significance, okay, the p-value here is less than our level of significance of 5%, which means we are going to be rejecting the null hypothesis. So the way we're going to write this is that we have sufficient evidence have sufficient evidence to support the claim that fewer than 30% of adults sleepwalked, which in essence is a rejection of the null hypothesis in favor of the alternative, which is a 100% completely valid conclusion. Should probably emphasize. The exact method of doing this, which we could do so as well. Only problem with the exact method is it's kind of a conservative value measurement. But the left-tailed test for the p-value is the probability of x or fewer successes among n trials, and right-tailed test is the p-value is the probability of x or more successes among n trials. The two-tailed test, the p-value is twice the smaller of the preceding left-tailed and right-tailed values. And for example of this, in testing a method of gender selection, 10 randomly selected couples are treated with the method. They each have a baby, and none of the babies are goals. Use a 0.05 significance level to test the claim that with this method, the probability of a baby being a goal is greater than 0.75. So for this, we need to test n times p. So 0.9 times 10. This is going to give us a value of, excuse me, it's not 0.9, 0.75. Let me very quickly fix that. Because otherwise this is not going to make too much sense. 0.75 times 10, this gives a value of 7.5. That's greater than 5. For n times q, we would have 0.25 times 10. This gives us a value of 2.5. And as such, that's less than 10. So, technically speaking, this should not be used. Despite the fact it's a simple random sample, it's still a binomial. Right? Simple random sample. This is still a binomial experiment. But we cannot say the approximately normal requirement due to this 2.5. So it's not approximately normal. And as such, we should not even be using this. But I'm going to just continue running the test just for the sake of an example of it. So the hypothesis statements, H naught is that P is equal to 0.75, and the alternative is that P is greater than 0.75. And this uses the probability that we have x greater than or equal to 9. And if we were to toss this into the binomial calculation, this would give us a value of 0.24402252. This gave us the a value of p of 0.75, sample size equal to 10, number of successes as 9, that type of thing. So because of this value being 0.2440252, because of this, we could say at the 5% level of significance, this value is greater than 5%. It would be greater than 5% if we put it into the normal calculator as well. But the 5% level of significance, there is not sufficient evidence to support the claim that with the gender selection method, the probability of a goal is greater than 0.75. We can also apply a simple continuity correction. This improves the conservative behavior of the exact method with an adjustment to the p-value that is obtained by subtracting from it the value that is 1/2 the binomial probability of the boundary. So in a right-tailed test, this would be the p-value is equal to the probability of x or fewer minus 1/2 of the probability of exactly x. Left-tailed test is the p-value is the probability of x or more minus 1/2 the probability of exactly x. And the two-tailed test is the p-value is equal to twice the smaller of the preceding left minus the tailed minus twice the smaller of the preceding left-tailed and right-tailed values. Thank you.